Hey everyone, welcome to another video about cloud and beyond. And this time we are on week 4 already and we'll be discussing cloud architectures. So what we can see in this slide is a blueprint. So a blueprint shows how a building is designed before it's constructed. So it can include the rooms and their layouts, electricity and plumbing, structural components, and how everything connects and functions together. Similarly, cloud architecture is a design plan of how cloud system is structured and operates. So cloud architecture is basically our blueprint. The hardware and the software are the materials that we use, and two systems can use the exact same materials, but it can be designed very differently. And that design is what determines whether the system holds up under pressure or falls apart. Now, for this visual presentation, we'll be discussing about the benefits of cloud architecture to businesses, and we will be discussing the 8 core architectural patterns or foundations, and two of them we'll be discussing in depth, which is the service load balancing architecture and the redundant storage architecture. Now, for the first question that we'll be answering is the business benefit of cloud architecture. So, before any architectures get designed, someone in the business has to justify the investment. So, what makes cloud computing compelling from a business perspective? So, first and foremost, the budget benefit of it is that it will reduce the capital expenditure. Traditional infrastructure before, you need to buy hardware upfront. You need to buy your servers, the racks, networking equipment before a single user even was served. So cloud eliminates that. You only pay for what you use, and it removes the financial barrier for startups and large enterprises because you don't need to invest on an upfront IT infrastructure that you may not be even using. Instead, you can invest in cloud that you can only pay for what you are using. Now, it is related on demand scalability as well. So, on premise systems, they are sized for peak load, but they are very wasteful at the rest of the time since it's not been um like you're not using it on its own full potential. So cloud lets you scale resources up when demand rises and release them when it drops. So you are never over or under provision. So one example is that if you are an online shop or an online retailer and you handle 10 times normal traffic on Black Friday, so if you're in the cloud, you can scale up automatically for that day and scale back down by Monday, which you only pay for what resources that you have used. Next one, high availability and reliability. So come from the redundancy built into the architecture itself. So when one component fails, another takes over automatically without human intervention. So there's no disruption and it is always available 99.99% at the time. Next one, so we also have optimized resource utilization. So there's no wasted capacity because resources are only used when needed. We have simplified operation. So we have this concept called abstraction. So this is provided by cloud provider because they handle most of the complexity and users interact through simple API so they can fetch the database inquiries without needing to understand every complexity behind it. Next one is auto recovery and fault tolerance. So if there's a failed system, you can automatically replace it without manual intervention. Cloud also offers geographic flexibility, meaning that um, you can deploy globally without setting up physical infrastructure. And granular billing, it ensures that the users are charged only for the exact resources they consume. Now, let's be concrete about what cloud is actually replacing. So, traditional IC had a set of very real and very painful problems, and cloud architecture is essentially an answer to each one. So, if you need more servers in the old world, procurement could take weeks, but in the cloud, you can spin up 1,000 servers in minutes. So, if you need like industrial strength services like databases or queries, instead of building and maintaining them by yourself, you can access them through simple APIs. So coordinating distributed jobs used to be a nightmare because you need to make custom ships and you need to have like manual effort. But the cloud hides the complexity. The scalability logic is subtracted away. No more manual failover when a server crashes because the cloud handles it automatically, and no more being stuck with over or under provisioned capacity because you can scale dynamically. And when you're done with the resources, you can basically release it. So it is easier to decommission. You don't have to have like a idle hardware waste or like thousands of servers lying around just because you don't need it anymore. Because you only pay for what you use, and yes, there's like zero waste. Now we move on to cloud architecture. So, how does cloud actually achieve all of these benefits? So, from cloud architectural patterns that has been established. Now let's walk through them. First one is workload distribution. So you probably heard it as like load balancing. So instead of one server handling everything, a load balancer spreads requests evenly across multiple identical servers. So we call it like horizontal scaling in action. So as we have discussed before, horizontal scaling is when you add or remove resources dynamical not dynamically. I mean it can be, but add or more resources as a feature of a cloud computing. Now we got resource pooling. So rather than assigning dedicated machine to each task, you can um group resources like CPU, memory, or storage into like a shared pools that can be allocated on demand, and this is much more efficient. So for dynamic scalability, so the system watches predefined condition that you can set, meaning say that you can set that if the CPU usage hits 80%, can automatically add or remove resources. Can be horizontal, meaning more instances you can add or remove resources or service. Vertical, which means bigger instances, you can increase or decrease a resource like CPU, storage, or even relocating workloads. So if you mean relocating, means that you can send a server to a like much better host that can handle the traffic. So for one is elastic revision resource capacity. So the cloud can provision or reclaim virtual CPUs and RAM in real time. So just like a processing demand shift, you can elastically provision the resources so it can be done without human intervention. It will automatically like provision the virtual CPUs and RAMs for immediate response. Next one is service load balancing. It's like a targeted version of workload distribution, but this one's for cloud services. I will be discussing this a bit later. Then we got cloud bursting. It's like a hybrid pattern. You run on premise normally, but when you hit capacity limits, you burst workloads to the cloud temporarily, then pull back. So the example that I've used earlier is the Black Friday sale. So if an online retailer have an on-premise servers, meaning that their servers is inside their business or like they're using it like locally or like privately, they can shift into cloud services if there's like a burst when like Black Friday say happened, and then they can just go back to normal operations on their own servers. So cloud bursting is good um, if you are more concerned about security, because on-premises resources is usually secured, but if you go into cloud, there's like some vulnerabilities that could happen then. So yeah, we got elastic disk provisioning. So it's like elastic resource provisioning, but for storage. We got redundant storage as well, like duplicate cloud storage with failover. We will discuss it a bit later. Now we go about service load balancing architecture. So it is the most commonly used patterns in real-world cloud system. The core idea is that you deploy multiple identical copies of the same cloud service across different virtual servers. A load balancer sits in front, intercepts incoming requests, and distributes them across those copies so no single server bursts a full workload. So this is a lot of information to take in, but I will give you an analogy that will further simplify what service load balancing architecture really means. So example is a call center has many agents. So when you call, the system routes you to a free agent. And if one agent is on a long call, you go to another. So the service is always available. So there's like a 2 points that you need to remember here, redundancy and smart routing. So you got multiple copies of the same cloud services running at the same time, and it is routed by your load balancer, so requests are spread across copies automatically. Now we got two patterns here. How do I don't know if I can point out in here, but as you can see at pattern A, we got the external load balancer approach, meaning that we have a load balancer specifically to be a load balancer. So all consumer requests go through a dedicated load balancer component, and then they route them to the right virtual service. So it's like that's like it is that is where the service load balancing architecture is commonly used is with an external load balancer. So the load balancer intercepts the message in the traffics to evenly distribute it to other virtual servers. But there's another pattern that we must discuss, which is the built-in server logic. So the service itself has built-in logic to forward requests to neighboring instances. So you can see there's no load balancer that will intercept. Will directly go to virtual server A, and it can distribute it to virtual server B or virtual server C, depends on how many or how much of the workload there is. So there's a key mechanism involved with using built-in service logic, which is a cloud usage monitor. So it tracks how hard each instance is working. And we had resource cluster running in active mode, so all nodes share the load, and resource application that spins up new instances when demand requires it. So basically, in built-in service logic, you got no load balancer. It is built in on your actual service, and it will distribute evenly to themselves if what needs to be distributed, so everything will work as efficiently as possible. We got redundant storage architecture. So this is about resilience. So the setup is pretty straightforward. You have a primary storage service and a secondary one. So the secondary is continuously synced with the primary via storage replication system. So under normal condition, all requests go to primary. However, when the primary fails, a storage service gateway detects this and automatically redirects all requests to the secondary. Now, the secondary device then serves the data through logical unit numbers, which are essentially virtual storage blocks. The consumer keeps accessing their data without interruption, and they may not even know if the over happened. So basically, redundant storage architecture is like having a backup data of like having a backup copy of all your data ready to take over if your main backup fails or your main one fails. Like keeping a backup copy of your photos on an external hard drive. So if your laptop dies, you haven't lost anything because it is an external hard drive. So if it's in the cloud per se, the storage service gateway switches the backup automatically. So basically, what happened in redundant storage architecture is you have two storage. You got primary and secondary. So primary storage is your main storage. It handles all normal requests, and it replicates, or there's like a copy continuously synced to the secondary storage. And when a failover happens, the gateway instantly redirects all your traffic to secondary. So this is what I've just discussed earlier. You got primary region, secondary region, but sometimes just needs to be a geo replication because some instances that um there's some instances that example you got um your primary data center in Sydney and you got your secondary data center is in Melbourne and they are very close to each other. So what happens if there's something like God forbid a war happens in Australia, like both of your primary and secondary region will not be available and it will reduce the availability of your servers. Yeah. So as you can see here, you got normal operations, primary active and secondary sync. So if a cloud consumer go to a storage service gateway, it will reach the primary storage. Then the primary storage is syncing to the secondary storage and it is on standby. You have both logical units serving and LUN sync. But what happens if there's a failover? The cloud consumer, the storage service gateway, it will redirect it to the secondary. Secondary storage is now the active one. It will be serving the data. It will not be synced with the primary storage since the primary storage is unavailable. And it will um, stores the data on LUN. So what happened is that um, if there's a normal operation, your primary storage is routinely replicated to the secondary storage device. If there's a failure detected, the primary storage becomes unavailable and it will automatically send all requests to your secondary storage. And it will have a continuity and you will not even recognize that there's a failure because it will the storage service gateway will automatically send it to you. Now, one thing that you need to consider about redundant storage architecture is that um, cloud providers they place secondary storage in different geographic region. So, for example, you got one in Sydney and you got one in Singapore. It makes economic sense because it can protect against regional disaster like power outages or floods, but it raises legal concerns. So, under Australian privacy law, personal data may be restricted from leaving the country. So, if your storage is overseas, you could be in breach of data sovereignty regulations. So, even though the data is just sitting there as a backup, it's still a real compliance issue that the organization needs to deal with. And also the replication, it depends on how far the two storage are because some some storages have like very far distance like continents even and it can affect the latency or how fast you can access the data because they have a very far distance against each other. And I guess that's it for week 4. Thanks for listening.